Hi dear students, this is Bhausar Sonone, Assistant Professor, Department of Chemistry, Gokhale Education Society's Arts, Commerce and Science College, Jawar District, Palagar. Dear friends, in the last part of the video, we particularly discussed about the solutions and particularly we have studied about the vapor pressure and the composition of an ideal solution and we tried to derive the equation for the Rod's law. Dear friends, in the last part of the video, we have also discussed some numerical based upon the Rod's law and we tried to solve these numericals. Dear friends, today in this part of the video, we are going to talk about the ideal solution. How can we define the ideal solutions? At the same time, here, today in this part of the video, we are going to talk about the equation of chemical potential for ideal solution and we are interested here to derive the equation for Rod's law, because if you remember about the last lecture, then we tried to define the ideal solution and non-ideal solution as the solution which obeys the Rod's law at all conditions of temperature and pressure as well as concentration. Then the solution is called as the ideal solution. Today also here you can see, here we are able to define the ideal solution. So what is the ideal solution here? The ideal solution is the solution in which Rod's law is obeyed by each and every component as its mole fraction varies between 0 to 1. So here simply we can say that the solution in which its component obeys the Rod's law, then the solution is called as the ideal solution. And here suppose we will consider the ideal solution which consists of the two component liquid A and the component liquid B, and the liquid and the vapor phase are in equilibrium with each other, and also we will assume that the vapor phase behave as the ideal gas. It means that it will follow the ideal gas equation PV is equal to nRT. So here we will consider the only one component of this system, that is component liquid A. So here the chemical potential of solution and the vapor are equal as it is in the condition of equilibrium. So here for the equilibrium system, the chemical potential of liquid A in solution is always equal to the chemical potential of the liquid in vapor phase. So for component A or the molecule A in vapor phase which behave as the ideal gas, the free energy of this component is equal to G of that molecule in vapor phase is equal to Gibbs free energy of molecule in standard Gibbs free energy of that molecule plus RT ln of PA upon P0. So this PA, it is the equilibrium vapor pressure of A above the solution, and P0 is the vapor pressure at standard condition, means for 1 bar pressure. So this, whenever we will replace this Gibbs free energy by chemical potential, this Gm by mu m and G0m by mu 0m, this mu m and mu 0m, these are the chemical potential at equilibrium and at standard condition, and this PA pressure is equal to 1 bar, then we will get the equation that is nothing but the chemical potential of molecule A in vapor phase equal to chemical potential of A at standard condition plus RT ln of PA upon P, equilibrium vapor pressure of A above the solution divided by vapor pressure of A at standard condition. So for molecule A in a solution, this equation, from the equation 1 A, the chemical potential of A in solution is always equal to the chemical potential of A in vapor phase, and that's why instead of mu A vapor we can write mu A of solution. So this equation 2 can be written as, here chemical potential of A in solution is equal to chemical potential of A at standard condition plus RT ln of P upon P0. So for pure liquids which is in equilibrium with its vapor, this mu A star is equal to mu 0 of A plus RT ln of P star upon PA, and this star indicates the pure component. So here chemical potential of pure component A is equal to standard chemical potential of A plus RT ln of P star. P star again nothing but the pressure of pure component A divided by PA, which is the total pressure. So in this way we are having the equation number 3 and equation number 4, and if we will subtract the equation number 4 from 3, that is this equation minus this equation, then we will get the equation that is chemical potential of A in solution minus chemical potential of A in pure state plus is equal to RT ln of PA upon P0 minus RT ln of P star A divided by P0, and definitely RT ln of this RT ln is the RT is the constant, ln of A minus ln of B is equal to ln of A upon B will become this P0, and P0 will get cancelled. Simply we will have the P upon P star A. So in this way, this is the chemical potential of A in solution minus chemical potential of pure molecule A, and this is equal to RT ln of P upon P star. So in this case, if as here we consider that the idea that is this vapor of this solution or the vapor of this compound behave as the ideal gas equation, or it is behave ideal, so it follows the ideal gas equation. So here as it is the ideal, it means it follows the Raoult's law, and you know very well the Raoult's law is equal to P is equal to XA into P0 A, or P star A means the partial vapor pressure is always equal to the sum is always equal to the product of mole fraction of component into the this P star into the total pressure. So this is the simple case, and Raoult's law is the limiting law, and this liquids is in real solution which obeys the Raoult's law. So we can put this equation of Raoult's law in the equation of 5. So instead of PA we can put XA into P star A. So this P star A and P star A will get cancelled, and this equation 5 simply can be written as that that is this mu will be transferred here, and that is chemical potential of A in solution is equal to chemical potential of pure molecule A plus RT ln of XA, and this is the chemical potential, or this is the equation for chemical potential of ideal solution. It's very simple, and this chemical potential of component in an ideal solution is it means that this equation 6 indicates that the chemical potential of component in an ideal solution is related to what? Is related to the chemical potential of its pure liquid form and its mole fraction, that is XA. So here there are some characteristics of the ideal solution. In the ideal solution, if the two components are there, component A and the component B, then in such system the interaction between AA, BB and AB are all in equal in strength. Again, the heat of solution in ideal system will be 0, and the mixing of A and B is completely random, and this system obeys the Raoult's law of vapor pressure, and the activity of each component in ideal system is always equal to its mole fraction under all conditions of temperature, pressure and the concentrations. So it's very simple. So this is the equation for chemical potential of ideal solution or the ideal system. It's very simple, and latter part is not too much important. I hope you can skip it. The next part is the vapor pressure composition and temperature composition of completely immiscible liquids. So completely immiscible liquids. In this case, suppose we will consider the two liquids which are completely immiscible, just like the water and the oil. These are the completely immiscible with each other. And whenever these are heated, their miscibility changes or their immiscibility changes, and due to this, the pressure due to vapor continuously increases. Whenever this system contains the two liquids which are completely immiscible are heated, then the pressure due to their vapors continuously increases. At a certain temperature, the total partial pressure of A and B becomes equal to the atmospheric pressure. Then this temperature is called as the boiling point of that system. If the solution has higher vapor pressure, definitely it will boil at a lower temperature. Hence the graph can be drawn between the vapor pressure composition of the solution, and there are three possibilities for this completely immiscible system. In the first case, the vapor pressure changes continuously with the composition of the mixture, and here you can observe here this diagram shows a pure component A having the lowest vapor pressure. This is the because this actually indicates the vapor pressure, and the pure component B indicates the higher vapor pressure. And whenever we will compare their boiling point based upon their vapor pressure, you know very well, if the vapor pressure is lower, the boiling point will be greater, and if the vapor pressure is greater, definitely the boiling point will be lower. So in this case, this pure component A is having lower vapor pressure, it means it will have the higher boiling point, and another pure component B is having higher vapor pressure, it means that it will having the lower boiling point. So this can be shown here, and you can observe here as the pure component A is having the lower vapor pressure, that's why it has the higher boiling point. Here it is indicated by this point, and here pure component B is having the higher vapor pressure, that's why it has the lower boiling point. This is nothing but the way in which the pure A will having highest boiling point and the pure B component will have the lowest boiling point, and the mixture of these two A and B will have the extremes, as B is more volatile, vapor pressure is more volatile, so its vapor pressure will be higher at any temperature than the A, hence the vapor pressure curve will be above the liquid phase. So this is the vapor pressure curve of B. So and this phase this line indicates the liquid phase, and this line indicates the vapor pressure. So this is regarding with the first case in which the vapor pressure continuously increases with the change in composition. In the second case, the vapor pressure shows maximum point in its vapor pressure composition curve, and that's why the solution will boil at the lowest. So there is some temperature or there is some point in its vapor pressure which indicates the highest point, and that's why it will boil at the lowest temperature. So here what is this? Here you can see here this is the pure component A having the lower vapor pressure, and pure component B is having the higher vapor pressure. What happens actually, their vapor pressure changes according to the with the change in temperature. But at point C what happens? At point C, the liquid and vapor phase have the same composition. Liquid phase and the vapor phase have the same composition, and they boil at a constant temperature T and will distill out over completely without any change in the composition. And this mixture, or this is called as a constant boiling mixture, or it is called as isotropic mixture. So at point C, here this is constant boiling mixture, and this is called as the, here you can see this is the lowest temperature at which the liquid and the vapor phase having the same composition, and this composition, and this is the boiling point at which the composition of both the phase remains same, and this constant boiling mixture is called as isotopes. It's not no important fractional distillation. In the type 3, what happens? Again, in the vapor pressure composition curve, the mixture of these two components A and B, in which A is having the lower vapor pressure, B is having the vapor pressure, and on this vapor pressure composition curve, they got some lowest point or the lowest of the curve at which the composition of liquid phase and the composition of vapor phase is in equilibrium, is same, and this at this point the liquid will show the constant boiling, and and that's why at point C, as it is having the minimum vapor pressure, that's why it will have the maximum boiling point. So here you can say, so here the vapor pressure shows minimum in its vapor pressure composition curve, and the solution at point C will boil at highest temperature, and the boiling point curve will show the maximum, and the vapor pressure curve will be above the liquid composition curve, and point C is called constant boiling composition, and this is least volatile. It's very simple to discuss how we can divide the systems based upon their change in vapor pressure or the boiling point with the change in composition. So this is very simple in case of completely immiscible systems to discuss the boiling point or the variation of vapor pressure or the variation of their boiling point with the composition. So dear friends, in the next part of the video We will discuss something about the ideal systems, particularly something about the non-ideal system that we also call as the real system, and what are the different characteristics of real solutions or the real system. Definitely these real systems as are called as the non-ideal solution. Definitely this solution will not follow the Rawls law, and that solutions will show the deviation from the Rawls law. So what type of the deviations are shown by this non-ideal solution from the Rawls law, that we will discuss in the next part of the video. Thank you very much.